pure maths. Don't worry, it's going to be a last talk again, but I guarantee this is going to be one of the most picturesque and beautiful parts of mathematics. So if you inspect this title, the one word I hope you're familiar with is a billiard. In the mathematical abstraction sense, we picture a billiard as just a table and a ball bouncing around. Like that. Took me an hour to animate. Anyway, if you look at every bounce, something must be obeyed. And that, as simple as it gets, is the law of reflection. It just says, you come in one way, you come out another, but you make the same angle with the side you hit. In the ideal world, if we turn off friction so the ball can go on forever, you might get something like this. The ball starts bouncing around a few times and goes on forever. Like, I didn't really draw everything, but up to here. Changes the starting condition a little, you get another pattern. This naturally brings us to the idea of a mathematical billiard. It is just a point mass bouncing inside a region, any region in space, at unit speed, which just says it never stops. With that in mind, you might ask, what's a triangular billiard? Well, as much as I love this scene, my summer research wasn't spent watching this all the time. Triangle billiard. Anyway, a triangular billiard actually is just a point bouncing inside a triangle. However, unlike its rectangular brethren, which I just showed you, this simple setup can give you a wide array of behaviors. Some might blow your mind. You can visualize such a billiard problem at home rather simply. You bring a laser and maybe a glass prism. I have a laser cut one across the street from the engineering department. You can make a prism, and if it's in a really dark room and you have a well-trained eye, you might get something like this. You can see the path of light bouncing around as if it's a billiard ball. Anyway, we'll get to that picture later. Most of the time, or sometimes, you can get very simple behaviors, what we call periodic. That just means it will close up on itself and start retracing. We define periodicity. It's just after finite many iterations, or sometime, you start repeating your prior steps. However, some other times, you get a thing that's ergodic or chaotic, as in the billiard path will never repeat itself, and eventually, any point you pick inside the triangle, it will get arbitrarily close. That's what we call, they will cover the whole triangle. This is the first few thousand iterations I plotted for one of the chaotic billiards. And it never repeats itself. It just goes on and on. I think this is a good opportunity for me to lead you to appreciate this concept of chaos in mathematics. Formally defined here. Not really formally, but I put it in italics, that's the definition. Also, this background, you can readily see it, it's just a zoomed in picture of the previous triangle billiard. Chaos is just a class of seemingly random, but in its heart, well-defined mathematical behaviors. In this case, just the reflection law applied once after another. You get this kind of behavior. So this is what I appreciate about this problem. It lives at the intersection of geometry and dynamics, and what's important to me, it leads to the applied side of mathematics, namely quantum chaos theory and quantum optics. So in the billiard problem, there is this long-standing conjecture that nobody has been able to prove. For 2 centuries, well, there was an anecdote about one physics professor in the 1970s brought this to a meeting, and his colleagues remarked, we can prove this in a week. But nothing actually happened from that time and even earlier to now. We don't know if every single triangle is home to a periodic billiard path. Let's go back a little to survey the landscape of things. If you recall the high school or middle school mathematics, you might be very familiar with the classification of 2-dimensional Euclidean triangles. They can be acute, with 3 small angles that are all smaller than 90 degrees. They can be obtuse, with 1 angle bigger than 90 degrees. They can be right, with 1 angle exactly equal to 90 degrees. And as I will try to motivate you, the case of a billiard varies dramatically for those three cases. Well, the behavior of a billiard varies dramatically for those three cases. Let's go to the simplest one, the acute triangles, for which a lot is actually known. About 300 years ago, there was this Italian mathematician, Fagnano. He was studying a seemingly different problem, but he accidentally proved that every acute triangle is home to a periodic billiard path. And the way to construct it is very simple. You take the three vertices of the triangle, the blue ones, and you draw the three altitudes. I think I pressed the wrong button, but you draw the three altitudes, like that, and you join the 3 feet of the altitudes. The black triangle you get, surprisingly, satisfies the law of reflection, and hence is a billiard path. And this works for every acute triangle, as I plotted here. You start from the equilateral of 80 degrees, you push one edge over, and for ease of your understanding, I've made a video. The black one being a billiard path. It lives in every acute triangle as we survey through the land. And what's more remarkable is that if you even slightly change the starting point, but keep your same angle, you will still get a billiard path, just slightly longer. And one classical tool we usually employ to understand such behavior is called unfolding. Recall the law of reflection. The light comes in, does some math, bounces around. But an equally valid way to represent a law of reflection is that instead of reflecting the light ray, we reflect the whole world such that the light ray can continue as a straight line. And this is the idea of unfolding. We can represent a billiard path as in the order that it hits every edge. We can represent it like this. Also, this is easy proof. Every billiard path that's periodic is one-to-one corresponds to a straight segment connecting corresponding points after a translation. So that black path, which I just showed you a few slides prior, is really just this yellow segment. However, I also recall, I just said this method fails for other triangles. Do you want to know why?
Yes.
Okay. So this construction, I hit all the 8 lines, but recall, it requires you to draw the 3 altitudes of the big triangle to find the three points defining the black triangle. However, for obtuse triangles, those 3 heights intersect outside your original triangle. Therefore, you cannot construct such an easy orbit. Is that convincing enough? A small question mark, suggesting that I haven't proved this conjecture either, but this is the build-up. In a similar fashion, many proofs suggested by people in the literature, their method always treats the 2 kinds of triangles very difficultly, and most of the time, actually, in all cases I've come across, they tread very difficultly for obtuse triangles. So this is when I considered, let's do something different. Let's try numerical methods on such an elegant geometry problem. So the idea is, if we find a triangle that's very close to the boundary of 90 degrees, that has a periodic orbit. Some periodic orbits, I must say, look very, very complicated compared to the one that I just showed you. And if we change one of the angles slightly and push the whole triangle to make it obtuse, what will happen to all the periodic orbits it hosts? Will they simply disappear? If so, why? And if they don't, voila, we got a new result. Also, this is, as a theoretical person, this is my first concrete coding experience. So I'm quite proud of what we'll be able to do over the summer. The main idea is abstraction. Instead of applying the law of reflection to light rays every time and over, and instead of looking at all the segments and being dazzled, we study a well-defined, hopefully, algebraic problem that we construct as such. First, notice that in this problem, the size of the triangle doesn't really matter. So we can just pick the two base angles of any triangle that uniquely determines the billiard table. And I chose to use two state variables to determine which, to log or to let the computer know which point we are visiting. And those are the C and theta. C is like a postcode. It tells you where you just landed along the perimeter, which conveniently are mapped to the open segments 0 to 1, 1 to 2, and 2 to 3. And theta is just the angle your light ray makes with the positive x direction. I chose that angle for computational performance and nothing else. Well, if you want to do law of reflection, the more reasonable angle you use is actually the incident angle. But performance is more important when you want to do 10,000 iterations or so. So with this setup, we can construct, if you want, actually a matrix linear algebra problem that just stipulates after we apply our triangular maps such and such times, we better come back to our initial condition. And that's a successful translation of what we just defined as periodicity to something that the computer can understand. So this changes what humans might do, just testing all the possible starting conditions and looking for periodicity, to something we can automate. So this is still an ongoing effort, but I think lays the foundation to something quite cool we can do in the future. And everything I'll be able to do, every figure you have seen this presentation were generated by my own software. It's available on GitHub. If you want to try it, here's the link. And here's the sample user interface I've been able to achieve. It gives you the initial conditions, draws the triangle, and does the specified amount of billiard iterations. Down here is automatic dynamical analysis. This one being shown is something called the Birkhoff-Poincaré map. It's nothing strange in my setup. It's just a plot of theta against C. And what else I can do is calculate the Lyapunov exponent. Again, nothing to be afraid of. The Lyapunov exponent just is a number that characterizes how quickly the butterfly effect goes in a periodic system. Or if you like, how quickly 2 points that start really closely together drift apart. And although summer is over, this project hardly is. I am still in the work of polishing the continuation code, improving my performance, and hopefully I'll reproduce and improve the published results in the literature. I guess this is the time for questions. Or comments? Did my jokes work? I was just asked, what's the practical application of this? Cool. Okay, I conveniently have this road sign here. Billiard problem is surprisingly, the mathematical billiard is a surprisingly versatile tool to solve a whole range of dynamical problems, or even if you have the mind to abstract, it can solve a lot of real-world problems too. Although the only thing I'm going to give you is still in theoretical physics, you might be able to picture it being helpful in the real world. So, has anybody watched the video from 3 Blue 1 Brown about 2 months ago? Or is anybody aware of this channel? Mm-hmm. Okay. In which, yeah, he used the billiard to compute pi. That was, again, not really practical, right? Okay, sure. Another very profound connection of this problem to real-world dynamics is if you have two masses sliding on a frictionless segment with two walls on the end, and you plot the velocity versus time graphs of those two masses, what you'll get is actually a periodic orbit inside a right triangle. This correspondence was really surprising back in the days, that this alone got me motivated to try to do something to help solve this problem. And more concretely, in quantum optics, if you want to solve a Schrodinger's equation inside a triangular boundary, you will, very strangely, and nobody knows, well, as much as I am aware, very few people knows why, you will get something called quantum scar. That's just when the classical periodic orbits manifest themselves in the solution of a wave function. It's something that's really elegant, and I'm sorry that I didn't have a plot for that, but that's the closest to the real world this problem can get, I guess. And thanks to you, thanks to my supervisor and the group who supported me immensely. And if you want to learn more, I have one article on my blog and my source software on GitHub. Thanks very much.